Chapter 6 in our textbook deviates significantly from the main lines of attack to differential equations that we've done so far, mostly, of course, focused on understanding the phase plane and qualitative aspects of thinking about the phase plane, as well as algebraic techniques where we're guessing and using eigenvalues and eigenvectors and so forth. In Chapter 6, the title is called Laplace Transforms. And as I just said a minute ago, it's a pretty different subject than what we're used to. We're still dealing with differential equations, of course, but it's a pretty different approach to trying to solve differential equations. I think it's really interesting and will be a nice change of pace for you, but be prepared to be doing some different kinds of things. And what I'll do is I'll start with an example of a differential equation. We'll make it a first order equation, and we'll make it linear. Let's make it dy dt equals, let's say negative 2y plus e to the negative 3t. Okay, it's been a while actually since you've thought about that kind of equation. That's actually a chapter 1 equation. It's first order, scalar. And if you reach back into your brain, you realize that we had a couple methods for attacking things like that. We could either use integrating factors or essentially guess and check, the method of undetermined coefficients. We want to come up with the homogeneous solution, the solution to the associated homogeneous equation, and then find a particular solution by guessing, and add those two together to get the general solution of this non-homogeneous equation. I'm going to go ahead and also add an initial condition. Let's say y of 0 equals 2, I'll pick. And so again, our goal would be then to find a unique solution to this initial value problem. All right, what's the Laplace transform about? Well, the Laplace transform is an example of a linear operator. Now, in the Mathematica notebooks, you've read about linear operators. They are functions that take functions as input and give you functions as output. Now, that seems a little strange to say it that way, and that's why we use the word transform or operator, so that we aren't saying function too many times. But they really are functions. They're mappings, things that take input and give you output, but the inputs and outputs themselves are functions. And what we end up doing with the Laplace transform in the broad perspective is we take our differential equations and we take the Laplace transform of both sides. Go back up here to the screen, and the Laplace transform as a symbol is quite often denoted by this pretty cursive L. It's always fun to make cursive L's. That is going to be the symbol, or one of the symbols, for the Laplace transform function, the Laplace transform that we plug functions into this. And if I apply this function, this operator, this transform to both sides of this differential equation, what do I get? Well, if I apply it to the left-hand side, I get the Laplace transform of the left-hand side, L of dy dt. And if I take it to the Laplace transform of the right-hand side, well, I get L of negative 2y plus e to the negative 3t. Now keep in mind, this thing was a differential equation, so everything is a function of t ultimately. And so ultimately we're equating the Laplace transforms of two functions of t. Unknown functions, because we don't know y yet. I said the Laplace transform is a linear operator, so it satisfies a linearity property, a linearity principle. Here I have a linear combination of functions, negative 2 times y plus really 1 times e to the negative 3t. Linearity says, well, L of the sum is the sum of the L's. Forgot my negative 2. And then this constant, negative 2, can be, in a sense, factored out. That's another property of linearity. I take out the negative 2 to write it this way. Now I haven't, keep in mind here, you might be confused, I haven't actually told you what L is yet. I haven't told you what it is except to say it's called the Laplace transform and it's linear. But what's the broad perspective of what's going to happen here? Well, the beautiful thing about Laplace transform, besides the fact that they're linear, is that this left-hand side, it'll turn out that will simplify to something involving the unknown function y, but not its derivative anymore. It'll involve the Laplace transform of y, and what we'll end up with is an algebra equation that we can solve pretty easily for the Laplace transform of y. So we'll get the Laplace transform of y, ultimately we'll get the Laplace transform of y equals something. And then, to find y, we'll take what's called the inverse Laplace transform of both sides of this. L inverse, can you see that okay? I'm trying a different color here, but that's not coming out very nice. That's actually not black, though it probably looks that way to you. It's supposed to be green. And there it looks a little bit better. We'll take the inverse Laplace transform of both sides of this equation. And as you might guess by looking at this thing, the Laplace transform and the inverse Laplace transform are inverse functions, inverse operators. They're going to cancel, leaving you with a y. And so we'll have our solution. Y will be equal to the inverse Laplace transform of whatever's over here, which will be the same thing as whatever's over here. So in a nutshell, that's the big picture of what's going on here. And now we got to get into the details. The details are, I guess you might say, less pleasant, but they're still kind of fun in a weird way, I think. First of all, what is the Laplace transform of a function? The Laplace transform of a function of t will be defined in the following way. It's a very strange way. We take the integral from 0 to infinity of the given function f of t times e to the negative s times t dt. Told you it was strange. What in the world's going on here? Well, let's just think about it in a purely symbolic way here, in terms of what's going to happen. First of all, note that it is an improper integral, so technically speaking, we have to think about issues of convergence or divergence, like you learned about in Calculus 2 for improper integrals. And e to the negative st, if s is positive at least, is going to be a function that decays towards 0 pretty rapidly as t increases. So that's looking good. It looks good. The fact that you have this here means it's probably going to converge, but it does depend on how big, in a sense, f of t is, in terms of whether this improper integral is going to converge. Suffice it to say that it will quite often converge. We're integrating with respect to t here, but we have this extra variable s in there, meaning that ultimately the thing we get is going to depend on that extra variable s. This thing is going to be a function of s. And so the Laplace transform of our original function of t is also going to be a function of s. Sometimes that's emphasized by putting an of s right here. Though oftentimes we don't bother doing that, partially because we're lazy and partially because it leads to confusion for people. But this Laplace transform of this function of t, we will treat it as a function of a new variable that we called s. Now the letter s is arbitrary. We could have used a different letter, but that's the letter that's traditional to use. Another bit of notation, because this new function is related to the old one being called little f, The new one we might call, well, big F of this new variable s. And we might call it big F of s at the start. More consistently with what our book does, if we take the Laplace transform of y, where y is an unknown function of t, that will give us a function of s that we'll call capital Y of s. Okay, so a little, this is a strange idea, strange notation, and so it takes some getting used to, but it's really not that bad once you get used to it. So that's what it is. That's definitely not clear that would definitely help you solve differential equations, but amazingly it does, as we will see as we go along here. But let's find the Laplace transform of some functions. How about the Laplace transform of the simplest non-zero function that I can think of, the constant function 1? What's the Laplace transform of the constant function 1? Going back to the definition on the previous slide, I'd have to do this integral. Improper integral from 0 to infinity of 1 times e to the negative st dt. Do that improper integral, and let's be nitpicky about it. Technically speaking, that's a limit of proper integrals, as the upper limit of integration goes to infinity. Improper integrals are not true definite integrals in the original sense that you learn about integrals. They're limits of definite integrals, assuming the limit exists. And if the limit doesn't exist, then the improper integral is said to diverge. All right, well, proper integrals like this can definitely be done. I'll just carry the limit sign along for the ride. Think about it here. You might want to think in terms of a substitution, but think of the s as just a fixed number, a fixed but unknown number. You do a substitution, for example, like u equals st, so du would be s dt. The variable of integration is t, and think of this s as just a constant. And if you do that, you'll see that what you end up with for the antiderivative of e to the negative st will be negative 1 over s e to the negative st. I'll let you fill in those details. T gets evaluated from 0 to b. All right, keep going. Plug in b in place of t. You get negative 1 over s e to the negative sb. Can't seem to make this not be a little bit blurry. Hopefully it's coming out okay. What do you think? Looks pretty good? Just zoom in if you need to. And then minus what we get when we plug in t equals 0, minus negative 1 over s e to the 0, which will ultimately be a plus 1 over s, since e to the 0 is 1. So now we need to think about the limit of this thing as b goes to infinity. Does this function of b, if you will, converge as b goes to infinity? Does it have a limit? Does it have a horizontal asymptote as a function of b? It depends on what s is. Certainly s can't be 0. We'd be dividing by 0. S also can't be negative, because if s is negative, then negative s is positive. We'd have a positive number times b here, and e to a positive number times b definitely does not have a horizontal asymptote as b goes to plus infinity. It does as b goes to minus infinity, but not as b goes to plus infinity. If s is positive, this will have a limit of 0 as b goes to plus infinity. So this whole thing ends up equaling 0 plus 1 over s, or just 1 over s, as long as s is greater than 0. Oh, I don't know if that's worth. Whoa, what happened? We're in another room. Well, that's the perils of not reserving a room at Bethel. It was an open room, but we got kicked out because another class had it reserved. Oh well. Where were we? We were trying to find the Laplace transform of the constant function 1. And here's what we got. 1 over s if s is greater than 0. All right, well, let's try another example. What's the Laplace transform of the function t? By definition, it's this integral, which will be a function of s, ultimately. Oh, and to do that integral, we need to use the dreaded integration by parts. Not really a u substitution, but integration by parts. We want to let u equal t and dv equal e to the negative st dt. Or if you use the Hughes-Howard book here on Bethel's campus, they would just call that v prime equals e to the negative st. But I'm used to calling it dv equals e to the negative st dt. This integration by parts is something you need to practice to remember how to do, and there's what we would get. And yeah, it's still an improper integral, so technically speaking, it's a limit as the upper limit of integration goes to infinity. And you might remember integration by parts in terms of u and dv is the integral of u dv equals uv minus the integral of v du. Okay? Now, I said that pretty fast, and maybe you are rusty on it and need to look it up, so you should maybe pause it and go look that up. But coming back to the problem itself, u times v is negative 1 over s times t e to the negative st. It's going to be evaluated from 0 to b. Then it's minus the integral of v du. I'm sorry my writing is getting slanted here, but that's what happens when I have to be on this side. Minus the integral of v du. Actually, this 1 should be at 1 dt. V du is going to be negative 1 over s e to the negative st dt. And I can pull the negative 1 over s because it's constant with respect to the integration, so I really get a plus 1 over s integral from 0 to b of e to the negative st dt. Going kind of fast here. When you plug in 0 into this part here, it goes away because you plug in t equals 0 there. If you plug in t equals b, you get negative 1 over sb e to the negative sb. And that thing is going to go to 0 as b goes to infinity, as long as s is positive. Even though you've got a b there. Think about that. You would end up using L'Hopital's rule really to show that you may take it as a given that something like this is, if you plug in t equals b here, is going to go to 0 as b goes to infinity when s is positive. So this all becomes a 0 if s is positive. So we end up looking at this integral. And we're going to get another, let's carry the limit sign along. We're going to get another negative 1 over s involved, so we'll get negative 1 over s squared here ultimately, e to the negative st evaluated from 0 to b. And let's see, we've got to plug in t equals b. Ultimately, the part involving t equals b will go to 0 when s is positive, just like before. The only part that won't go to 0 is when we plug in 0, because we'll get e to the 0, which is 1. We'll be subtracting that. Ultimately, here we'll get a 1 over s squared if s is positive. Let me very quickly show you that you can check this on Mathematica. Just zoom in there. There's a built-in Laplace transform command. Smaller here. Plug in your function. I'll do the first example, the function 1. Plug in its variable t, and then plug in the variable you want for the Laplace transform, traditionally s. There we go. There's a confirmation of our first example, though you should realize that this is only when s is positive. That's not a real big deal as far as the differential equation application goes. And if I plug in the function t that we just did, there we go, we get 1 over s squared. The book's main example from section 6.1 is e to a power, e to the 2t, e to the 3t, or in general, e to the a times t, where a could be any constant. And the main result there is that the Laplace transform of e to the at is 1 over s minus a, would be the more traditional way to write it. That's a fundamental fact. Laplace transform of e to the at is 1 over s minus a. Technically, if s is greater than a, is the way that you should think of that fact. Okay? And this is a very important fact in this first section that you can then use to, for example, solve the differential equation. Remember this from the first slide? Okay, let's rewrite what we've got here. Rewrite that from that differential equation when we took the Laplace transform of both sides. We ultimately got this. And the Laplace transform of e to the negative 3t, by what we just found, the a is negative 3. So we're going to get 1 over s minus negative 3, which is really 1 over s plus 3, can be substituted in there. I mentioned that this thing here can be simplified too. And here's the result. It can be simplified to be in terms of a Laplace transform of y. The result is that it's is s times the Laplace transform of y minus y of 0. Okay, now that's actually one of the probably the most important fact of this section, and I'm just going to skim over it here. Something that you should read about. You should understand its derivation. Its derivation actually involves integration by parts, and some assumptions about the function y that it, for example, doesn't grow too big too fast. This is what you end up getting, and this is the key property that allows you to replace the differential equation with an algebra equation. We now have an algebra equation that we can solve for the Laplace transform of y. Y of 0 is the initial value. That was given to be 2 for this problem. So now it's just a matter of solving this algebra equation right here for the Laplace transform of y, and then taking the inverse Laplace transform. Still got some work to do, though. The inverse Laplace transform won't be so simple. It's a linear equation in Laplace transform of y. Let me isolate the Laplace transform of y. If I add 2 times the Laplace transform of y to both sides of this equation, it'll cancel on the right. And I'll be able to factor out a Laplace transform on the left side with an s plus 2 inside parentheses. Think about that for a minute. On the right side, I'm going to end up with everything that doesn't involve the Laplace transform of y, because I'm going to add 2 to both sides of this equation to get 2 plus 1 over s plus 3 on the right. Now I just divide both sides by s plus 2 to get this. That's the thing that I now take the inverse Laplace transform of both sides on. And the inverse Laplace transform turns out to be linear too, which means that you can write the inverse Laplace transform of the right-hand side like this. So how do you find the inverse Laplace transform of these functions? Well, this one is easy. It's just using this fact again, up at the top there. Because 1 over s plus 2 is 1 over s minus a, where a is negative 2. Since the Laplace transform of e to the at equals 1 over s minus a, the inverse Laplace transform of 1 over s minus a equals e to the at. It works the other way. So this inverse Laplace transform down here is e to the at, where a is going to be negative 2. It's going to be e to the negative 2t. But we're still left with this thing right there, and that's the hard part. And that's what we need to finish off with here. The key is to use another, well, technique from Calc 2, partial fractions. Yay, partial fractions. Oh, that's the pen doesn't work so well. Better not stray from blue. 1 over s plus 2 times s plus 3. I want to write that as a over s plus 2 plus b over s plus 3 and solve for a and b. Okay? You've done this before, okay? I'm not going to take the time to do it because I want to show you one more thing here. You can do it. You can solve for a and b. It's partial fractions. Multiply both sides by s plus 2 times s plus 3. Make appropriate cancellations. Get a system of equations for a and b that you can solve. There's a quick way to do it by plugging in special values of s, like negative 2 and negative 3 here would make it real simple to solve for a and b. When you take the inverse Laplace transform of this sum then, the inverse Laplace transform is linear. You're going to get the inverse Laplace transform of this plus the inverse Laplace transform of this. And once again, this fact right there will come to the rescue in this example. Okay, it won't come to the rescue in future sections, but in this first section of chapter 6, it'll come to the rescue. You get the answer. It's not so bad, okay? The whole method seems maybe unnecessary since we already know techniques for this equation. But we will see that there will be other equations where we need the Laplace transform, especially equations where this non-homogeneous part is even a discontinuous function, believe it or not. There will be a couple main examples in chapter 6 where that non-homogeneous part, that forcing function, if you will be discontinuous. And therefore, you definitely need the Laplace transform if you're going to solve the equation. The old methods won't work. What I want to end this video with is just to show you something neat that you will, especially if you're a physics and engineering major, see at some point in the future. There's something called the Fourier transform, which is similar to the Laplace transform, but harder. The full Fourier transform involves imaginary numbers. Surprise, surprise. But there are more specialized versions of the Fourier transform called the Fourier sine transform or the Fourier cosine transform. They're a little simpler. And Mathematica has built-in Fourier sine transform, Fourier cosine transform, Fourier transform commands. Here what I've done is I found the Fourier transform of the function e to the negative t over 10 times sine of a times t, where a is thought of as a constant here. Just like the Laplace transform, this gives you a new function in a new variable. The traditional variable for this is actually omega. And this beautiful thing right here ends up being, as a function of omega, the Fourier sine transform of my e to the negative t over 10 times sine of at. Real beautiful to look at, I'm sure. But what's more interesting is to think about what this means with some graphs. This is more interesting, but it is difficult. So I'm going to try to describe this real quickly, but I'm sure you won't really get it the first time through. You'll have to really think about it, maybe watch it a couple times, read the book's description about the Laplace transform version of this. These integral transforms are, in a sense, to try to understand them intuitively, they're a way of measuring how closely two functions match. The Laplace transform is a way of measuring how closely your function f of t matches e to the negative st for various values of s. The Fourier sine transform turns out, and I won't explain this other than just to say it, It's a way of measuring how much your given function here matches up well with sine of omega times t for various values of omega. Now I have this e to the negative t over 10 in here just to make the improper integral that defines this Fourier sine transform to converge. The main thing to focus on is on the sine of at. The question is, for various values of a, how does that match up with sine of omega t for various values of omega? And this graph down here is supposed to illustrate that, and that's the neat thing for this video. The red curve is the f of t, the e to the t, negative t over 10 times sine of at, and I'm changing a here so I get different values of a. The blue curve is sine of omega t, although I typed it in here just as a w to make it quicker. Sine of omega t for different values of omega. And where do the red and blue match up? Well, they match up when their periods are approximately the same. I'm starting them both at the origin. Right about there, their periods match up. This blue dot that you see right here, if you zoom in on that, that blue dot is the value of omega for the particular blue curve that's being drawn. You can see that this blue dot, when the curves match up pretty well, is close to where this purple curve has a peak. What's the purple curve? The purple curve is the Fourier sine transform. So its highest value is at the value of omega, where the blue and the red curves match up the best. The wellest, I was going to say. Match up the best. If I move omega to some other value, then they don't match up so well. But when I move it right about there, they match up pretty well. I'll change a again to something else. It could be over there. The Fourier sine transform shifted over. It's got a peak at a different spot. You can see that at this value of omega, they're not matched up. But if I move it over, just have to do that up here, to where the peak of the purple curve is, now you can see they match up pretty well. Okay, so that's an intuitive idea of what the Fourier sine transform is measuring. The Laplace transform is similar, though because you're matching it up with e to the negative at, it's maybe not quite as much fun to match up, but it is useful for solving differential equations, as are these Fourier transforms. That's the end of this video.